Okay, so the next topic up for discussion um, is how to do integrals like the one that you can see here that involve several different trig functions. And there's going to be several methods that we have to remember. Most of them involve using trig formulas that you already know or should have seen before in another math class to rewrite the integral in a form that is a little bit easier to integrate. So in this section, we're going to be using a lot of those ideas from trigonometry that it might have been a little bit of time since you've seen. Okay. But the main formula that we're going to use is this one here. When we're integrating functions of the form sine to the m power of x times cosine to the n power of x, the main formula that we're going to need is just the Pythagorean theorem, which hopefully everyone is super familiar with. It's the one that says sine squared of x plus cosine squared of x is equal to 1. And generally what we're going to do is move one of these two to the right-hand side and in order to replace powers of cosine or sine. So what I mean is cosine squared of x is equal to 1 minus sine squared of x, and vice versa, sine squared of x is equal to 1 minus cosine. 1 minus cosine squared of x. So this formula is going to let us transform powers of one function into powers of the other function. But the particular way that we do it, the particular thing that we transform, is going to depend a little bit on the exponents that we look at. So this first problem is relating to the case where m, the exponent on sine, is odd. And our strategy here is going to be to leave one of the one of the sines and transform the rest into cosines. Using, in this case, the second form. So you're going to start with sine to the m of x. You're going to break off one of them, and then the rest of them, in this case, m minus 1, is going to be even, and you're going to convert all of these into cosines using this formula for sine squared. So let's just do a problem to see how this works. One theme, I suppose you might say, of this particular section is that these integrals generally take a while, or at least a lot of writing, in order to figure out. So part of this section is getting comfortable working through long problems. And you'll see what I mean as we go along. So in this case, we're integrating sine to the third power of x times cosine to the fourth power of x. So we do have an odd power of sine, which means we need to break off one of them and convert the rest. So we'll have a sine times a sine squared in this case. So we're breaking this one up. And then we still have the cosine to the fourth power. Let's just put a line there for neatness. Okay, so like I said, we're going to use this formula to transform the sine squared in this case. So sine squared becomes 1 minus cosine squared. So the trick here, the idea behind our strategy, is that eventually we're going to do a u substitution where u equals cosine, and then du is going to be sine. So we've left one sine behind in order to become our du a little bit later on. But in order to get there, we'll have to first distribute here. So just multiply out, leaving the sine alone, because it's our du, like I said, in a few minutes. So distribute through, you get cosine to the fourth when you multiply by 1, and then you add powers of cosine to get minus cosine to the sixth power of x dx. And then we have a little bit of room over here where we can do our u substitution. Like I said, u is going to be cosine, and du will have a sine, and then of course dx tagged on for our differential. Okay. So this is the trick behind our strategy. So in the next step, we aren't going to have any trig functions left. The sine x and the dx will be collected together to become the du. And here we have a u to the fourth power minus u to the sixth power. And then the sine dx is du. Okay. So what is my antiderivative here? And just leave the u's in when you answer. Someone want to give it a try using the power rule?
1/5 u to the fifth and 1/7 u to the seventh.
Good. Yeah, so remember your minus sign, and then you'll have to add a constant on the end, since this is an indefinite integral. And then to finish off the problem, we need to rewrite our u's in terms of sine and cosine. So substitute back in. We'll have cosine to the fifth power and then cosine to the seventh power. And carry down your constant. Okay, so that's it. That's the problem. So does anyone have any questions about the strategy that we used? Okay, so let me just point out, I said before we started working that a common theme in this section is that the problems are going to take a bit more writing to work out than you might be used to. And you can see why, because there's several steps that we had to do before we could even get to a u substitution. We had to apply our strategy, breaking apart the power of sine. We had to do a substitution. We had to multiply out, and then we could finally get to our u substitution. So there's going to be several steps here to each integral that we do. Okay. So no questions before I flip the page to the next problem? So the next problem we're going to work on is a problem where n is odd. So remember, n is the power of cosine. We're looking at sine to the nx times cosine to the, I got this backwards, of course. Did I? Yeah, sine should have m to match it up with what I said earlier. There we go. So the power of cosine is now going to be odd. And the strategy is the same as before, except we're going to apply it to cosine. We're going to leave one cosine behind. And then break the rest off and transform them into sines. Again, using the Pythagorean theorem, but just the opposite version solved for cosine, which will be 1 minus sine squared. So in this particular integral that we're about to do, we can see that there aren't any powers of sine, actually. We just have an odd power of cosine. But it doesn't matter whether you actually have any sines in the original integral. We're going to add those in just a second. So we'll apply the strategy, break off one of the cosines, and then what we have left over is cosine to the fourth. Okay, so our formula, remember, is cosine squared equals 1 minus sine squared. So in order to use this formula for cosine squared, we're going to have to rewrite this even power of cosine as some power of cosine squared. And what I mean is this, in case it's not clear. Cosine to the fourth power is really cosine squared squared. So cosine squared times itself one time. Does that make sense to everyone? Or are there any questions over this step? Okay, so if there aren't any questions, what we're going to do now is our substitution. So instead of cosine squared of x, we're going to write 1 minus sine squared. And we can't forget that this whole thing should be squared, since that was on the outside of our parentheses there. So before we can go on any further, we'll have to multiply this out. Okay, so what do we get when we square this? Anyone want to give that a try? Remember, this is 1 minus sine squared times 1 minus sine squared. So you'll have to FOIL it, distribute. No one wants to volunteer. Okay, that's fine. I'll just work it out for us. So we have 1 times 1. That gives us just a single 1. And then we're going to get a minus sine squared and then a second minus sine squared. That'll give us minus 2 sine squared. And then finally, we'll multiply our negative sine squared times another minus sine squared, giving us plus sine to the 4th. Okay. And this is the point where we can see our u substitution. U is going to be sine, and then the corresponding du is cosine, or cosine dx, really. So let's write that over here. So this is just the opposite of what we did on the last example, as you might expect. So like I said, the cosine and the dx will be grouped together to become du. And then inside the parentheses, we have a 1 minus 2u squared. And then we have a plus u to the 4th. Then tag our du on at the end, our cosine x dx. Does someone want to try this integral here using the power rule?
Yeah, it's 1 minus 2/3 u cubed plus 1/5 u to the 5th.
Okay, you're really close. We needed a u for
I'm sorry, x,
first
my
one.
bad, x.
And u, remember, since we're integrating with respect to u. So u minus, and then the rest of it was correct. So 2/3 u cubed plus 1/5 u to the 5th plus c. Okay, so good work. Now we have one final step of substituting back in sine of x for u. So that's the answer there. Any questions over the second strategy for when our power of cosine is odd? Okay, so once again, as I mentioned earlier, the problems in this section take a little bit of effort to work out because we have several extra steps that we don't normally have in integrals of substituting, multiplying out before we can get to our u substitution. So when you're working through these on your homework, you will need a little bit of perseverance to get through all of these intermediate steps, but just stick with it. So no questions before we go to the next page? Okay, and there's one more strategy that we need to learn in order to deal with integrals for sine and cosine, powers of sine and cosine. And that's when both powers are even. So when neither of them are odd, we're going to need to do something a little bit different. And the trick here, uh, it's a little bit harder, I think, but not too much. It's just that we're going to have to convert everything into cosines using a different formula. Okay, so in order to do that, like I said, we will need a different formula. And these are called usually something like the double angle or half angle formulas, depending on their context. So this is the one that says sine squared is equal to 1 minus cosine of 2x over 2. And then the corresponding formula for cosine squared just has a plus sign, 1 plus cosine of 2x all over 2. So instead of the Pythagorean theorem, we'll need to use these other formulas from trigonometry. So using these two, we're going to be able to convert any even powers of sine and cosine into cosines, just cosines. And we'll see how that plays out in this next example. Here we're trying to find an antiderivative for sine to the fourth of x times cosine squared of x. So we do have two even powers. And we're going to have to do something a little bit like we did on the last example, where we need a sine squared and not a sine to the fourth. So we need to rewrite this even power of sine as a power of sine squared. So sine squared times sine squared is sine to the fourth. Multiply the two powers. So this is what we're working with. And we're going to use both of these formulas and substitute in. And I'm going to have to give myself a little bit more room. So I'll put my equal sign back over here. Sine squared of x becomes 1 minus cosine of 2x over 2. And we have a square here. So remember to copy that down as well. And then the cosine squared becomes 1 plus cosine of 2x over 2. And this next step, what we're going to do after the substitution, is where I think these can be a little bit more challenging, and that's, well, multiplying out and then doing some additional simplification as necessary. So what we'll want to do, I think, first is to pull all of our constants out to the front. Here we have 1 over 2 squared. That'll give us a 1 over 4. And here we have another 1 over 2. So that means overall we need to factor out a 1 over 8. And let's just pull that totally outside of the integral in order to make things a little bit easier to read and easier to multiply out, to distribute. Basically, we want to get rid of our fractions. And now we have to distribute everything. We have to FOIL out everything here. And this again takes a little bit of writing and persistence. Remember, this is 1 minus cosine of 2x times 1 minus cosine of 2x. So if you work that out, you'll get a 1 minus 2 cosine of 2x. That's when you multiply the minus cosine of 2x times 1 twice. And then you'll have to multiply cosine of 2x by itself. So the minus sign goes away, and you get a plus cosine squared of 2x. But we're not done. We still have this guy. 1 plus cosine of 2x. So maybe I'll put a note here about what we're doing. We are distributing our multiplication. So keep at it. We now need to distribute this 3-term thing inside the parentheses with this 2-term one. So it's not really the FOIL method anymore, but it's similar. Everything needs to get multiplied. Maybe we'll write out all of it. So you need a 1 times 1 plus 1 times cosine of 2x. And then minus 2 cosine of 2x gets multiplied by 1. And then it gets multiplied by cosine of 2x. So we end up with a minus 2 cosine squared of 2x. And then we've dealt with the first 2 terms, one more to go. You multiply by 1. That's a cosine squared of 2x. And then you multiply by cosine of 2x, so you get a cosine cubed. That's a bit messy. Let's combine any like terms. We only have the one constant, but we do have a couple of cosines of 2x that we can combine. So 1 cosine of 2x minus 2 cosine of 2x is minus cosine of 2x. And then we have some cosine squareds that we can combine. That'll give us a minus cosine squared of 2x. And then finally, we have a cosine cubed. Okay, any questions so far? No? Okay. So far it's mostly been algebra. Now we need to do a little bit of calculus. We have 4 terms here. Let's break this integral up into pieces. So the 1 over 8 goes along with everything since it's on the outside of the integral. So we have an integral of 1 dx. Then we need minus 1 over 8 times the integral of cosine of 2x. Then we have a cosine squared of 2x. and then plus cosine cubed. So we need a plus 1 over 8 times the integral of cosine cubed of 2x. So two of these integrals we can do right away. The first two here. The other two require a little bit more effort. The integral of 1 is just x. The integral of cosine of 2x, you might have to think of a u substitution. You might be able to do this in your head. But the gist of the idea is that we'll have to divide through by 2, since there's a 2 inside of the cosine function. So we end up with a minus 1 over 16, and then sine of 2x. Okay, so that's the first two completed. The integrals have gone away. We'll have to do more work for this one. And I lost a 2 here. Should be a 2x inside of that. So what we're looking at here is an even power of cosine. That means we'll have to apply our strategy again for when we have even powers. Convert everything into cosines using these two formulas. Except now I have a cosine of 2x, cosine squared of 2x. So when I multiply by 2 again, I'll get a cosine of 4x. So let me write that out. We get a minus 1 over 8. And then inside of our integral, we now have 1 plus cosine of 4x over 2 dx. So does everyone understand where the 4 came from, since we started with the 2? Okay, and then this last integral, we have an odd power of cosine. That means we'll have to use our earlier strategy using the Pythagorean theorem. So we'll convert that into cosine times 1 minus sine. 1 minus sine squared, excuse me. Like so. And now we're actually able to finish off the problem fairly quickly now. Here we just have a 1 plus cosine. We'll have to do a small u substitution, but that's not a big deal. Over here, we do have to do another u substitution. U is going to be sine. And then du will be cosine x dx. Okay, so maybe we'll write one more step out and then finish off the integral. So you'll want to pull this half to the front so that you get another minus 1 over 16 here. And then 1 plus cosine of 4x inside. And then over here, plus 1 over 8. And then do the u substitution. That'll be 1 minus u squared du. And if you want to think about this as a u substitution, again, that's not a bad idea. Here our u would be 4x, and du would be, running out of space here, du would be 40x. So in the end, you'll have to divide through by 4 on this term because of that u substitution. And one more line will see us to the end, I think. So copy down the first bits that we have already done. From this integral, you'll get an x from the 1. And then from the cosine of 4x, you'll get a 1 over 4 sine of 4x. And I've just distributed this minus 1 over 16 to each term. And then over here, we'll get a u minus 1/3 u squared. So our u, in this case, remember, is sine. So that'll get us a 1 over 8 times sine. Let's see, and there was a small mistake up here that I didn't catch. Remember, we started with a cosine cubed of 2x, so we should have 2x's in all of these places. Unfortunately, that makes things look messy. Which means we actually had an extra 2 here that needs to come along for the ride. When we do our u substitution, we'll have to divide through by that 2 on this step. Unfortunately, I didn't catch that a second ago. Okay, so remember, our u is sine of 2x, and then we'll need, here we have to divide by 3. So bring the 1 over 16 along, and then a 1 over 3 sine of 2x cubed. And then just barely enough room here at the end for our plus c. Okay, so that problem took slightly longer than I expected it would, since we're a couple of minutes over time. But that's the idea. These things can take a while, as you just saw. We have to do a lot of work doing simplification, but we're just applying the same strategy, the same 2 or 3 strategies over and over again to get down to the answer. You could do a little bit more cleanup here at the end to combine like terms, but I think we'll just leave it like this for now. Okay.